Imagine yourself lying on a lush green meadow on a quiet summer night, a gentle breeze carrying the faint scent of wildflowers, and as you lift your head, you behold the night sky sparkling with billions of stars twinkling like diamonds scattered across a mysterious black velvet tapestry. In the vast Milky Way galaxy of ours, where more than 100 billion planets float suspended in infinite space, there exists a wondrous allure that stirs the depths of our hearts. Could there be some forms of intelligent life existing beyond the verdant blue planet we call home? The chorus of crickets chirping around you, the soft rustling of leaves in the wind, all serve as a reminder that life on Earth is both fragile and miraculous, yet they also propel us to dream of distant worlds far away. This is no fairy tale or idle daydream, but a profound question that science is tirelessly seeking to answer. With astronomers hunched over desks cluttered with data screens, their eyes alight with excitement each time telescopes capture new signals from the cosmos. Today, we shall embark together into this uncharted territory, exploring the potential for intelligent life on other planets, feeling the thrill as if unwrapping a secret gift from the universe itself. In the past, we have discussed the Fermi paradox, that stubborn riddle that keeps many awake at night. Given the high probability of millions of civilizations beyond Earth in this immense universe, why have we yet to detect any evidence? Why no contact with them? It is the stark contradiction between our blazing hopes and the cold silence echoing from space. But now, let us redirect our gaze, not merely pondering if intelligent life exists out there, but envisioning how we might stretch our hands across the colossal cosmic distances to touch it, like a child reaching to pluck a star from the heavens. Let us conjure images of innovative technologies slowly taking shape in laboratories aglow through the night, theoretical pathways that one day will propel humanity across the stars, with the roar of engines thundering powerfully and flashes of light streaking from the tails of spacecraft. Picture humans setting foot on a remote planet, strange winds whispering through spacesuits, and we ourselves becoming the very extraterrestrials we once yearned to encounter. This notion not only quickens the pulse with exhilaration but also reshapes our perception of our place in the grand cosmos, from humble creatures on a blue orb to bold explorers poised to take those monumental first steps, transforming the dream of interstellar travel into tangible reality, fueled by the conviction that the future awaits our bold unveiling. Recent advancements in astrobiology, as reported in scientific journals through 2025, further fuel this vision, with studies suggesting that microbial life could thrive in subsurface oceans not just on icy moons but potentially on rogue planets wandering the galaxy's fringes, expanding the canvas of possible habitats beyond traditional stellar systems. Even within our familiar solar system, where the sun radiates its warm glow and planets orbit like members of a grand family, the quest for extraterrestrial life feels more intimate and tangible, akin to digging in one's own backyard. Though encountering intelligent beings in this local neighborhood seems remote, much like spotting a friend in a teeming crowd, we brim with optimism about unearthing ancient microbes or even current life forms on nearby planets and moons. Mars, the fiery red planet etched with ancient river valleys twisting like scars of time, parched lake beds that once shimmered under sunlight, has long ignited our imaginations as a potential cradle of life, where perhaps gentle streams once murmured and tiny creatures swam in primordial waters. NASA's Perseverance rover, which landed in 2021 and continues to yield samples as of November 2025, has detected organic molecules in Jezero crater, hinting at past habitability and prompting plans for sample return missions by the early 2030s, where scientists hope to analyze these traces in Earth-based labs for definitive signs of ancient biology. Yet Mars is far from the sole contender in this solar system of chilly atmospheres and swirling red dust. Jupiter's moon Europa emerges as a captivating icy jewel, its surface encased in a gleaming shell under the faint light from the gas giant, slightly smaller than Earth's moon with a diameter of about 3,100 kilometers, equivalent to 1,900 miles. Europa orbits Jupiter at a distance of roughly 628 million kilometers, or 390 million miles from Earth, and beneath that thick icy crust, scientists believe lies a vast liquid water ocean, potentially twice the volume of all Earth's oceans combined, envisioning a shadowy yet promising watery realm where subsurface currents might lap against the frozen underside. This positions Europa as a prime target for astrobiological inquiry, with aspirations to detect life signatures in that moist environment. Complementing this, Enceladus, Saturn's moon, boasts geysers spewing water plumes rich in organic compounds, as observed by the Cassini mission. An ongoing analysis in 2025 suggests these could harbor hydrothermal vents similar to those fostering life in Earth's deep seas, broadening the search within our cosmic backyard. The Europa Clipper mission, meticulously prepared for launch in the coming years, with the latest updates as of November 2025 indicating a successful liftoff in October 2024 aboard a SpaceX Falcon Heavy rocket from Kennedy Space Center, is set to arrive at Jupiter in April 2030 after a journey involving gravity assists from Mars in March 2025 and Earth in December 2026. The spacecraft will conduct nearly 50 close flybys of Europa to gather intricate data, aiming to illuminate the enigmas of this frozen moon. Its primary objective is to ascertain whether the subsurface ocean provides habitable conditions, scrutinizing the ice shell with fractures resembling Earth's glacial rifts, where the underlying ocean may be warmed by tidal heating from Jupiter's gravitational pull, and even probing chemical compositions, geological features, along with plumes of icy water erupting from beneath the surface, towering hundreds of kilometers high and carrying pristine samples from the profound depths, like a cosmic offering delivered straight to our instruments. Instruments aboard, such as the radar for Europa assessment and sounding ocean to near surface, will penetrate up to 30 kilometers into the ice, mapping potential water pockets, while the Europa thermal emission imaging system will detect heat signatures that could indicate active geology supportive of life. However, probing Europa is no simple feat, brimming with hurdles that leave engineers scratching their heads during marathon meetings. The harsh radiation environment encircling Jupiter, with high-energy particles hurtling like an electromagnetic tempest, could fry or utterly demolish a lander robot in mere hours to days, even shielded robustly. Envision the invisible hum of that radiation, akin to thunder rumbling in silent space, rendering human exploration with current technology virtually impossible. A crewed mission to Europa would confront immense distances and lethal radiation perils, potentially inflicting severe internal damage on brave astronauts, causing sharp pains piercing through their protective suits, as simulations from NASA's 2025 radiation studies underscore the need for advanced shielding like water-filled habitats or magnetic deflectors. Thus, if scouting life within our own solar system proves so arduous, demanding patient endurance amid obstacles, how dare we aspire to one day traverse the entire galaxy's stars, where distances span light years and voyages stretch across centuries. Two principal avenues emerge to surmount these barriers, like twin trails winding through a dense forest toward distant horizons. The first is the concept of generation ships, colossal vessels akin to airborne cities sailing between stars at sublight speeds, potentially requiring hundreds to thousands of years to reach the nearest stars. The initial voyagers would age and pass away during that interminable trek, bequeathing the Odyssey to their descendants, with children's laughter echoing through corridors and tales of Earth recounted under artificial lights. This idea evokes visions of self-sustaining ecosystems aboard, complete with hydroponic farms, closed-loop recycling systems recycling every drop of water and breath of air, and psychological support frameworks to combat isolation, drawing from psychological studies on long-duration spaceflight conducted in analog habitats like HICs on Hawaii's volcanoes through 2025. Yet this vision carries shadows of concern, like storm clouds eclipsing optimism. Should the journey span generations, Earthbound technology might leap forward dramatically in the interim, with the latest from NASA and private firms like SpaceX in 2025 revealing reusable spacecraft and superior engines, rendering the generation ship obsolete or allowing a swifter successor to overtake and arrive first. This paradox prompts reflection on viability, questioning the wisdom of investing in a sluggish expedition when tomorrow might deliver grander surprises, such as breakthroughs in cryosleep or automated precursor probes that scout ahead without human frailty. Hence, the second path gleans more enticingly, enhancing propulsion systems to accelerate journeys, drawing hopes nearer. NASA has partnered with Lockheed Martin to design, build, and test nuclear-powered rockets, promising technology harnessing fission reactors to deliver potent thrust to engines, propelling vessels far swifter than conventional chemical fuels. Presently, a crewed flight to Mars demands about 7 months, but this innovation could slash that to at least 45 days, conjuring scenes of crews peering out windows to witness Mars swelling in view after mere weeks rather than half a year. Theoretically, a nuclear thermal propulsion system could attain peak velocities of approximately 22 kilometers per second. Lockheed Martin's 2025 updates highlight progress on the demonstration rocket for Agile Cislunar Operations project, though setbacks like the cancellation of DARPA's Draco in June 2025 due to technical hurdles have shifted focus to lunar surface reactors, with plans for a 100 kilowatt fission unit deployable by 2030 to power Artemis bases, indirectly advancing deep space propulsion tech. But more advanced blueprints promise even greater feats, such as designs employing magnetic fields to expel superheated plasma from engines, potentially achieving speeds up to 123,000 miles per hour, or 197,950 kilometers per hour, nearly 55 kilometers per second. Nonetheless, space's immensity renders even this modest. Reaching Alpha Centauri, our closest stellar neighbor, would still consume about 26,000 years, a figure that overwhelms with the universe's scale. Yet the notion of pulsed nuclear propulsion offers a beacon of promise, envisioning spacecraft surging to velocities approximating 13,411 kilometers per second, roughly 4.5% of light speed, permitting arrival at Alpha Centauri in about 100 years. Other theoretical constructs target 10% light speed, like solar sails harnessing photon pressure from sunlight or lasers, gentle yet forceful as winds billowing a vessel's canvas on oceanic swells. These sails, lightweight and expansive, could unfurl to square kilometers in area, gradually accelerating nanocraft over years, as prototyped in NASA's 2025 solar sail demonstrations. A standout endeavor is Breakthrough Starshot, an audacious initiative to craft minuscule nanocraft propelled to 20% light speed via potent Earth-based laser arrays, like a Titanic shot from desert tower installations. As of 2025, the project lingers in research phases amid reports of indefinite holds due to funding and technical snags, yet persists with laser trials and resilient nanomaterial developments, proposing a fleet of tiny starships to probe the Alpha Centauri system 4.3 light-years distant. Despite challenges like electronics enduring harsh space over decades, bombarded by interstellar dust akin to meteor showers, it remains our premier shot at stellar outreach, igniting fervor for inaugural snapshots from alien realms, with Caltech's January 2025 experiment scaling light sails to withstand pressures equivalent to multiple atmospheres. The odyssey to unearth extraterrestrial life grows captivating with Proxima Centauri b, an Earth-sized exoplanet nestled in the habitable zone of the red dwarf star Proxima Centauri, where liquid water might persist beneath the star's soft crimson glow. Unveiled in 2016 and scrutinized by the James Webb Space Telescope with fresh 2025 data hinting at atmospheric water vapor and potential biosignatures like dimethyl sulfide, this find has inflamed imaginations, suggesting we need not roam the galaxy's expanse to seek life. A proposed flyby mission at 15 to 20% light speed would span 20 to 30 years outbound, plus 4 more for signals to return, like a missive from afar. Though intelligent life on Proxima b seems improbable due to stellar flares, we turn to Gliese 667 cc, 23.62 light-years away. At 20% light speed, we arrive in 118 years. This super-Earth, massing more than our world yet slimmer than Uranus or Neptune, likely a rocky sphere with a dense atmosphere in the habitable zone, possibly retaining surface liquid water, the gateway to life. Envision its terrain laced with rivers and bizarre forests if conditions align, even fostering intelligent evolution, crowning it a premier prospect. Next comes TRAPPIST-1e, 40.7 light-years distant, demanding over 200 years at 1/5 light speed. Orbiting an ultra-cool dwarf star with temperatures permitting liquid water, Earth-sized amid a system of watery potentials, 2025 telescope observations reveal TRAPPIST-1's more stable flares than anticipated, enhancing life's outlook with visions of shimmering seas and aquatic beings, a beacon guiding discovery. The system's 7 rocky worlds, 3 in the habitable zone, offer a multiplanetary laboratory for comparative exoplanetology. Then Kepler 186f, 580 light-years in Cygnus, circling a steady red dwarf. If its denizens peered at Earth through telescopes, they would glimpse the year 1444, pre-Columbian Americas, temporal vista pondering history. Earth-sized in the habitable zone with liquid water promise, its star's longevity fosters stable milieux for complex life. Yet at 20% light speed, the voyage claims 2,900 years, underscoring needs for superior observatories like next-generation telescopes probing atmospheres for oxygen or methane. Finally, Kepler 22b, 640 light-years off, larger than Earth with expansive atmospheres and vast ocean potentials. The trek devours 3,200 years at that pace, beyond current grasp, spurring innovations like the Alcubierre drive, a theoretical warp-bending spacetime for superluminal jaunts, though demanding universe-surpassing energies. Yet 2025 studies from applied physics propose feasible subluminal variants using positive energy densities, sans exotic matter, hinting at warp tech in centuries ahead. These vast gulfs remind us of humanity's humility yet latent might, primed to conquer the cosmos with inspired hearts, as fresh Fermi-paradox theories in 2025, like the radical mundanity positing bored aliens ceasing broadcasts or the dark forest hypothesis of wary civilizations, deepen the enigma while stoking our resolve to listen and reach out.